Find the domain and range for each graph below. So in this example, you can see that there are two graphs. Over here on the left is function f, and over here on the right is function g. And we're asked to find the domain and range for each. So if you will recall, the domain is a set of x values. So when we try to find the domain of this particular graph, we're trying to just report back which x values does this graph cover. Well, we always start with the smallest number possible. So if we start as far left as we can, that'll get us the smallest number. It looks like the graph starts right here. And if we follow that up, the very first x value, or the smallest x value here, is -2. And in fact, we will include that -2. And so we travel along this graph to find out where the graph stops. So how far right, or what's the largest x value the graph attains. And the graph stops going right here, which has an x value of 1, 2, 3, 4, 5. So that is where the graph stops, -2 to 5. This is the domain for f. And we can do the same thing for the range here. The range starts at the smallest y value and goes until the largest y value. So in both cases, going from smallest number to largest number, you just have to know whether or not you're reporting back an x or a y. So domain are the x's, which means range will be the y's. So the lowest y value here is -6, and as you travel along this graph upward, the highest y value here, the biggest y value, is 3. So -6 to 3 will be the range for that particular graph. And then using the similar ideas over here with this particular function, the smallest x value to the largest x value, and the smallest y value, or the bottom of the graph, to the largest y value, you can see that the domain and range are -2 to 6 for the domain and 0 to 4 for the range. And one thing I want you to notice here also is that I'm using square brackets, and that's because on these particular graphs, there are no open circles. So if one of the values that you found had an open circle, there's a chance that you may be using parentheses here instead of square brackets. Find the domain and range for each graph below. In this particular example, we just have this one graph here. And we get to talk a little bit more about the intricacies of how to find a domain and range for a function. The first thing we will try to find here will be the domain. So I'll write D. And for the domain here, we do want to start as far left as the graph starts. So the smallest x value this graph exists at is -4. So here's how I'm going to do this. I'm going to write -4, and I mentioned earlier, if there was an open dot, we will have to use a parenthesis here instead of a square bracket. Now something interesting happens with this domain. The domain doesn't care about vertical jumps like this. We just need to know, is there an x value here when x equals 0? So as you're traveling along from -4 to 0, everything looks good. But then at 0, there's a closed dot, which means x is allowed to equal 0. And way down here, there's an open dot, which means x is not allowed to equal 0. Which one do you pick? Well, it doesn't matter if you have a bunch of open dots on the same vertical line. As long as you have a closed dot on that vertical line, the function is allowed to have an x value equal to 0. But from here, the graph continues all the way over to 2 as far as the domain is concerned. So the first bit of the domain is -4 to 2. What domain is concerned about is horizontal gaps. So you can see here between 2 and 3, there's a horizontal gap. X cannot equal 2.5, 2.25, 2.999. It can't equal any of those, but X is allowed to equal 3. So we have to start a new interval over here that X is allowed to be equal to 3. And if you follow this all the way over, the graph stops going to the right when X equals 6. But there's another open dot here. So we will have to use a parenthesis. And so now that we have two different intervals for the domain, we have to join them together with a union. So there is the domain for this graph, and we're going to use a similar idea to figure out what the range is. The range starts with the lowest y value, or if you like, the bottom of the graph. So it looks like this graph starts way down here at -5, as far as the y value is concerned. And we can travel up. And I want to stop right here at -2. You can see at -2 that there are two open dots. But you can see right here the rest of this little linear part and this closed dot right here at 4, -2, that since that allows the function to have a y value of -2, the graph or the function is allowed to have y values equal to -2. So we can continue traveling up, and it looks like just for this little piece right here, it stops at y equals -1. So the range here will be -5 to -1. We will include the -5 and the -1. And that's because right here, when the y values equals -1, there's no open dot. So we just make it a square bracket. But then there's this horizontal gap between y equals -1 and y equals +1. This one here. There's no function happening in this band right here. So we cannot include that in the range. So we have to start another piece of the range. The range starts here at 1 and goes up to 4. There will be a parenthesis and a square bracket. So we will need to join these together with 1 to 4 like this. So here's the domain and range for this particular graph. Let f of x equal -2x squared plus 3x minus 4. Find and simplify the difference quotient for f of x. That being said, you should probably know what the difference quotient is. So the difference quotient, I'm just going to call dq for f of x, is equal to f of x plus h minus f of x all over h. So one of the first things that you need to do in order to figure out the difference quotient for a function is first find f of x plus h. Well, luckily, you'll be given a function every time, so we already know what f of x is. F of x equals -2x squared plus 3x minus 4. So f of x plus h is what you get when all of the x's are replaced with x plus h. We just come over here and we write -2. This x won't be here anymore. It'll be x plus h squared plus 3 times x plus h minus 4. Now with this particular expression here, you'll have to distribute x plus h to x plus h, which is multiplied out over here. But then you'll still have to multiply everything here by -2. So I'm going to write the next line here. This will be -2 times x squared plus 2xh plus h squared. And you can also distribute this 3, so plus 3x plus 3h minus 4. And when you distribute this -2 through everything here, you'll get negative 2x squared minus 4xh plus h squared plus 3x plus 3h minus 4. So right here is what you get when you simplify f of x plus h. And as far as I know, none of these terms can be combined. So now we turn back to the difference quotient, this fraction right here. F of x plus h is all of this. So I'm going to write that. I'm going to write negative 2x squared minus 4xh. Oops, I did not distribute correctly up here, but this is a negative 2h squared. So I forgot to distribute the negative 2 right here. I've corrected it in this step. Plus 3x not squared, plus 3h minus 4. And from this, as you can see in the difference quotient, we will be subtracting f of x. So we will subtract, we already know what f of x is, that's negative 2x squared plus 3x minus 4. And then the very last thing up here is that we will divide all of that difference by h. So all of that will be over h. So what's really nice about this is that any term without an h will cancel away in the top. So negative 2x squared at the beginning, subtracting a negative 2x squared, if you subtract something from itself, it turns into 0. And the same thing here with positive 3x minus positive 3x and negative 4 minus a negative 4, leaving us just with some terms that are left over from the first set of parentheses here. So that will be negative 4xh minus 2h squared plus 3h all over h. So this entire fraction here nicely reduced to this fraction here. Now that all the terms that are left have an h in them, we need to get the h out of there. And you do that by common factoring. So I'll common factor an h, which leaves you with a negative 4x minus 2h plus 3. Still all over h. And now the h's cancel and the top and bottom, leaving you with negative 4x minus 2h plus 3. There is the difference quotient for this particular function, f of x. Find the domain. On this slide, we have 3 different examples. You can see we have A, B, and C. And I put B down here. I'll explain that in a minute, and C right here. So in order to find the domain of these different functions, we need to follow where the square roots are and which numbers are in the denominator. For example, in example A, we know that whatever number gets inputted here for x, we can't end up with anything that's negative inside the square root. So what we'll do here is we will look at 3 minus x, because that's what's inside the square root, and we need it to be bigger than or equal to 0. And if you subtract 3 from both sides and divide both sides by negative 1, you'll end up seeing that x needs to be less than or equal to 3. So you can test that. You can pick any number x that is less than 3, say 2. 3 minus 2 is 1. That works. It's positive 1. Or you could pick negative 1. 3 minus a negative 1 is positive 4. So yeah, you can take the square root of a positive 4. Or any number in between there, as long as it's less than negative 3. So we have that restriction from the numerator. In the denominator, if there is a denominator, you need to set it equal to 0 and solve for x. Actually, I think we need to set it not equal to 0. So we can be any number as long as x is less than or equal to 3. But we also need to check that denominator, so x plus 5 cannot equal 0, which means that x cannot equal negative 5. Ooh, that's good information to know. We can be less than 3, as long as we're not equal to negative 5. That's what these two different things are telling me right here. So we have two different conditions, so I'm going to be writing this in interval notation. So if you want to be less than 3, or less than or equal to 3, well, I know that means that you can be negative infinity, but you can be equal to 3 on the other end. And this is a huge gap in here for this interval notation because I have to reach in and pull out the number negative 5. So I'm going to say you can start at negative infinity and go all the way over to negative 5 as long as you don't equal negative 5, because that's what this is telling you. I can hop over the number negative 5 and start right on the other side of it. And there's the interval notation. Or you can write something like this. You can be all real numbers, x is less than or equal to 3, and x cannot equal negative 5. These both mean the same thing. So here are the domains, the two different ways to write the domain for example A. Now example B, there's no denominator, so we don't have to worry about that. And this is not a square root, this is a cube root. So if you are trying to find the domain and there are cube roots involved, and there's nothing in the denominator, then your answer is all real numbers. There are no restrictions here. So part B, pretty easy here. And lastly over here, part C, this function only has a denominator and no square root anywhere, so we don't have to consider a square root. We just have to take the denominator, 2x squared minus 5x minus 12, and set it to be not equal to 0. So when you factor this, you'll end up with 2x plus 3 times x minus 4 cannot equal 0. And then you can take each one of these little linear factors and set it to be not equal to 0. Not equal 0, there we go. And when you solve each of these, you'll get x cannot equal negative 3 over 2 and x cannot equal positive 4. So you can stop there and say all real numbers except x cannot equal negative 3 over 2 and x cannot equal 4. Or if you like interval notation, you can write negative infinity to infinity, right? It's all real numbers, I'm just interpreting this. Except x is not allowed to equal negative 3 over 2, so it can't equal negative 3 over 2, and it cannot equal 4. And there's the interval notation version of the domain. If P is a point on the graph of a function, find the corresponding point on the graph of the given function. P is a point on the graph of a function f. Find the corresponding point on the graph of the new given function. So in part A, we have a point that is negative 2 comma 4. And this is what the new function looks like. This is y equals 1/2 of the function of x minus 3 minus 4. In order to figure out where the new point is, I think it's easiest to work with the y values first. So the y value here is 4. And when you look over here at this function, the values that are taking place outside of the function affect the y value of the point. And since 1/2 is being multiplied to the function and 4 is being subtracted from the function, this acts very normally, and you will want to just follow the order of operations to figure out where this new point is, where the new y value is. So the first thing that we're going to want to do here is take the 4 and multiply it by 1/2. Because what this does is it takes the y value, multiplies by 1/2, first, and that's a 2. So then we're going to take this 2, and from here we will subtract 4, leaving you with a new y value of -2. For the x value, it ends up being just a little bit stranger, and that is because we don't just apply this inside to the x coordinate. What you do is you set this inside equal to the x coordinate, and that will allow you to find what the new x coordinate will be. So what's inside the function over here is x minus 3, and we want that to equal -2. And when you solve for this x, you will get x equals 1. And that is the new x coordinate for the ordered pair. Now on this other example, we have a brand new point, -2, 1, but we're going to follow exactly the same reasonings here. We will look at everything happening outside, so this -3 and this -5. Now the -3 is being multiplied, so we will take the y coordinate, we will take 1, we will multiply it by -3, and we will subtract 5. This gives a new y coordinate of -8. And with the x coordinate, -2, you can set this x coordinate, -2, equal to what's on the inside of this function, 2x. And if you solve for x here, that tells you x equals -1. And there's the ordered pair, or the new point for this transformed function here.